Hello. Okay, it's time to get started. Welcome back, everyone. Great to see you again, well, in whichever form. So, as you requested, I have set up the class for this course, and I saw that several of you have signed up, but I think one of you emailed me and said that he was unable to sign up. So, I'm not sure what the problem is, but apparently if some of you succeeded, it should be okay, right? So, I see right now 7 people enrolled in class. Is there anybody here who tried to sign up and couldn't? Or let me know if the problem persists. We'll try to fix it from there. It was a struggle, but I managed it. What kind of struggle? Why it was not okay? Interesting. Link didn't take me to the class page. Okay, let's see. So it's Sheila Atchison. Let's see if I have it here. Yeah, I think it should be. I think I saw it here. Yeah. Okay, so I'll look into this again today, but basically the class link is this, so maybe we can try it right now. So this is the class link. Same here, it took me the generic Piazza page. Interesting. So if you click on that, so can somebody else try it? So if you click on that link, you don't get to the course yet, right? It works. Huh. I don't know, maybe it just something. It worked. Good. I'm glad. Yes. Now, also, I think we should fix time for our office hours. So I propose the following sort of schedule. So we'll have one office hour, or 2 hours during the week, say maybe on Wednesdays, so maybe today, and then additionally on Friday, we'll have discussions and office hours. So I was thinking to have a discussion. So since you guys signed up to different classes, we'll have 2 discussions at 10 and at 12, and then it will be sort of a mixture of discussion and office hours. So since everybody will be present, we'll solve some problems, and then I will hear you out about your questions and problems. So perhaps it will be the best way to kind of combine everybody's needs. And in addition, we'll have office hours. So today and every Wednesday, I'll also put a link. I put an announcement on B courses, office hours today and every Wednesday. At 2 p.m. Pacific time. So if you cannot make 2 p.m., send me a message. I'll try to meet with you later or earlier or something like that. Yeah. So maybe later. If you say you are in Asia, for example, right? I think the time difference is like 8 hours plus another day, right? So I can maybe join in the evening, and then it will be your morning. Okay. Does it sound good? And additional office hours. So we can call it Q&A session on Fridays. So this is the deal. Okay. Great. Right, so let's continue with our lecture. So last time we talked about, oh yeah, so I forgot the math prank problem. So what's the fun problem for today? You can think about it anytime. Actually, maybe I can type it, right? So nah, probably not a good idea. So the problem is find the pattern in the following sequence: 0, 1, 2, 3. That gives 1. 0, 8, 2, 1. That gives 3. 1, 5, 8, 2. That gives 2. 2, 7, 8, 9. That gives 3. 1, 1, 7, 0. That gives 1. So what will be 8, 8, 4, 0? Question mark. Okay, so you probably knew it. So Amok get the answer. Okay, so Amok says the answer is 5, but don't explain it to everybody, to anybody. So yeah, so the answer is correct, but let me not explain the idea. Right? So claim that there's a pattern in this well in this list. You need to recognize it and find which number corresponds to 8,840. Okay, so you can think about this in the back of your mind. Right, so yeah, so we ended with the cycloid. Let's revise it in our memory. Yeah, so the cycloid is the curve that is formed by a ladybug that sits on top of your tire. Well, not on the very top, because otherwise it will get squished. So anyhow, you make a chalk mark on the tire, and then you start driving. Forward or backward doesn't matter. And we get this red curve over here. Right, so last time we have found its parametric equation. So here theta is the parameter the theta is the parameter that well, parameterizes, that gives the functions x and y. So here they are. So we allow theta to vary between negative infinity and plus infinity, so that will give us an infinite cycloid in both directions. We have also studied its tangent lines, right? So the way it works is that you can. So I remind you that the formula for the derivative in parametric description of the curve looks like this, right? So it's the dy over dx is equal to dy over d theta divided by dx over d theta. And a simple calculation leaves us with sine theta over 1 minus cosine theta. And then we can ask ourselves, what is the possible range of the angles which the tangent line forms at various points of the cycloid? And turns out that it becomes horizontal at on top of those humps, right, as expected, and it becomes vertical at those troughs, right? So at those troughs, there are cusps, and then when the point approaches the cusp from the left, the derivative is negative infinity. When it approaches from the right, the derivative is positive infinity. Yeah, and we have found the locations of those minima and of those maxima and the cusps. Are there any questions about this? Okay, so then, okay, now, if you want, you can copy this in your note or notebook or somewhere, because I will soon move below. Okay, so now let's continue talking about this curve. Now let's find the area under this. Let's find the area under the cycloid. But first, let's remind ourselves how areas work. So for a function of a single variable, and so you have some function, f of x, right? And as x changes between a and b, right? You can ask yourself, what is the value of the area between the graph of the function, and then vertical lines x equals a, x equals b, and the x-axis. And of course, we'll know that the answer is given by the definite integral. And so this area equals integral from a to b, f of x dx. And according to the fundamental theorem of calculus, it is equal to the difference of antiderivatives at point B and antiderivative at point A. So here, capital F of x is a function such that its derivative is equal to f of x. Recall that an antiderivative is defined up to a constant, right? So, and to use this calculation, we are free to pick any antiderivative. Any value of the constant is okay because it gets canceled out here. Now, a couple of warnings. You should apply this formula with care, right? You cannot just bluntly take a function, integrate it like this, and then just subtract one from another and declare that the answer will be area, right? So the integral, of course, always makes sense, well, if the function is integrable, but consider this situation. Consider a graph like that. We know it, right? So since we're talking about parametric curves, we're not bound by having single-valued functions in our disposal. So say you look at this thing, right? And then your point A, the point A is here, your point B is there, and then, well, you want to integrate this guy. Yeah. You want to integrate this function from A to B. Well, you can certainly do that, but the answer, well, then you can ask yourself, what's the meaning of the answer, right? So it's kind of hard to even assign the meaning to it, right? So you'll get a, so since this is a multivariate function, right? If you treat it as a function of one variable, well, then the geometric meaning of this integral doesn't even make sense. However, what makes sense is the parametric version of it, right? So remember that if you start from, so say the curve is parameterized such that the parameter t, you write it as x equals x of t and y equals y of t. So you travel like this, right? And then, so say this is point A, right? And then this is point B. So for example, we can say that, how should I do it? Yeah, so let's say A has coordinates x sub A and y sub A, and B has coordinates x sub B and y sub B. So we can say that when t is equal to some t sub A, right, the x of t sub A equals xa, and the x of t sub b is equal to xb, and same with y, right? So y t sub a equals ya, y of t sub b is equal to yb. So then you can define what you want to do. You want to integrate from A to B, and the answer will actually be equal to the area 1 second. So the answer will be equal to the area of. I'll magnify the plot in a second. 1 second. Does this look better? Yeah. So well, as we can see, when x is equal to b, we have 3 points on the curve, right, where with the same value of x. So these 3 points have the same coordinate, the same x coordinate. However, they have, let's say, c, d, right? However, they all have different values of the parameter, right? So you can say that c is defined by x sub c, y sub c, right? And d is defined by x sub d, y sub d. So, and you're free to pick your, so in other words, it's up to you where you want to go. So if you want to calculate the area, which is now shaded in orange, right? Then you calculate, then you integrate from this point to that point, right? If you want to do something different, then you have to pick your point differently. So it was just a comment to show that if you have a parametric curve, which is not a single-valued function, which cannot be expressed as a single-valued function, then you have to be very careful. And certainly in examples that we'll see later, this will become important. Okay, I'm going to zoom back a little bit so we can have more space. Yeah, so we'll look at a calculation. Now, so first, let's see how this formula transforms if we decide that if you want to parameterize it in terms of a parameter, right? So if you say that the x is equal to x of t, then we know how to change variables in integral, right? So then this integral with the area, I'm just going to continue here. Well, let's start with a new line. So parametric formula for the area. And in fact, we can just consider this example here. So say t changes. Yeah, so let's say let x be equal to x of t, and then y is equal to y of t, and t varies between t sub a and t sub b. You can put alpha, beta, or a, b, doesn't matter. Excuse me. And then and exactly as in the situation here, right? So I'm just going to use this assignment. So let's say when x is equal to ta, we have it's equal to xa. When it's equal to tb, excuse me, it's equal to xb. So we want to integrate, and then this of course works regardless of whether we are computing area or not. It's just a change of variables in the integral. So integral from xa to xb, f of x dx, right, is equal to, and now we're making change of variables in integral. So if x is equal to x of t, then dx, the differential of x, is equal to the derivative x prime of t dt. So we're assuming that the function x of t is differentiable in the whole domain of definition. And then we can change the integrations by saying this is equal to integral from now ta to tb, because integral is now in terms of a new variable, f of x of t, x prime of t dt. Yeah, so I believe that you're familiar with this change of variables and under the integral. And yeah, so you can just evaluate it as an integral over the t variable. Okay, so let's look at an example. So we take I'm gonna just keep the formula up so we can look at it. Let's take our cycloid again. So, and let's calculate the area under one arc. So we start from, this is the change, this is the origin, right? This is the x-axis, this is the y-axis. Now, and let's remind ourselves, what was the height here? Oh, okay, before we go, there's oh yeah, so Yuan is answering the question about substitution. So yeah, so first of all, right, so we did two things. There were two places where we changed things, right? So first of all, we replaced dx with x prime dt. And second, because the new integral is now is done over t, we have to express the limits of integration in terms of t, right? So when t equals ta, x equals xa. So it's the same point on the plane, it just parameterized, it's described using two different languages, right? So one is one in terms of x and one in terms of t. Yeah, that's right. So when you have definite integrals and when you do change of variables, you always have to be careful to keep track of the limits of integration. So we have the cycloid, which had equations. Let me write down the equations again. X equals r times theta minus sine theta. Y is equal to r 1 minus cosine theta. And then for this particular example, let's say theta varies between 0 and 2 pi. Okay, so let's remind ourselves how this works. So what is the position of the maximum here? What is the value of the maximum? Two R. Yeah, okay. I'll get back to your questions in a moment. Let's fix this one, right? So 2R, and what's the coordinate of this point, of the end point of this arc? How far? What is this? 2 pi r. That's right. 2 pi r. So remember, that's exactly the circumference of your tire. So as you roll the tire once, it's like, it leaves a little bit of rubber on the pavement, and yeah. So this is 2 pi r. In fact, yes, I think let me answer questions about change of variables by doing this example, and then you guys can see if I still need to comment on that. So we want to find this area over here. Okay. Now, well, area equals integral. So here we're doing integral over x. So it's integral from 0 to 2 pi r, and then times this well, f of x dx. Well, and f is actually y, right? So let me just write y right away. So we won't have to introduce any more variables. Y of x times dx. Unfortunately, we don't have explicit formula of y in terms of x, right? So that would require some complicated trigonometric functions, and we do not want that. So instead, we're changing the variables to so we plug in terms of y, we plug in, instead of writing it as a y of x, we write it as a y of theta. right? And we write x as a x of theta. So it is equal to integral from 0 and now to 2 pi, right? Because this is the range in which theta varies. And now we write y as a function of theta times dx. And remember that dx we want to split as x prime of theta d theta. So we want to represent this as y of theta, and we want to represent the differential as x prime of theta d theta. So it's that times the derivative d over dt of r theta minus sine theta and everything d theta. So far so good? Okay. Yeah, so let's do the derivative. Integral from 0 to 2 pi r 1 minus cosine theta multiplied by r 1 minus cosine theta d theta. So that gives us integral from 0 to 2 pi r squared 1 minus cosine theta squared d theta. Why is it d over dt? Yeah, where did the t come? Oh, it's just the derivative. So this is the, I mean, I just wrote it. This is x prime of theta. Oh, the t, I'm sorry. Yeah, you're right. Excuse me. It should be theta. There is no t. Yeah, thank you. And yeah, so to do this integral, we just open up the parentheses, r squared as a constant, so we can take it up front. Take it up front. So that's integral 1 minus 2 cosine theta plus cosine squared theta d theta. Okay. Now, how shall we? I forgot how you how in calculus can someone explain how you figure out what the new bounds are after substitution? Well, so okay, let's get back to here. Let me write it here. So we know that x of 0 is equal to 0, Rohan, right? And we know that x of 2 pi r is equal to 2 pi. So it's literally before substitution, you are using these numbers, these values, and after substitution, you are using, sorry, I did something stupid, excuse me, that way around. Never mind, yes, x of 0 is equal to 0, this is true, but then x of 2 pi is equal to 2 pi r, right? So these are values of theta. So this is theta in the beginning, and this is theta in the end. And this is x in the beginning, this is x in the end. So your original integral was from 0 to 2 pi r, something dx, and then you replace it with integral from 0 to 2 pi, something d theta. Does that answer your question, Rohan? Sure. Okay, going back to the calculation. I mean, it should be, once you start doing the homework, and you'll see that the you'll get a handle on it. Okay, so how shall we do this integral? So we need to recall how to integrate cosine squared. What shall we do in this case? half angle. Yep, that's right. So there's the trig identity for half angle. So cosine squared of theta, you can write it as 1 plus cosine of the double angle divided by 2. Okay, and now if you plug it in back and then we integrate, so now we integrate over theta, we integrate 1, so that gives just the 2 pi, right? It's a constant. Then what happens when you integrate 2 cosine theta over the period? What is the integral of cosine theta from 0 to 2 pi? Zero, of course, right? So it's a periodic function, and if you integrate function over the period, you get 0 by definition, right? So look, I mean, you can do the formula for indeed. So it's true that integral of sine x dx from 0 to 2 pi is 0 integral 0 to 2 pi cosine x dx is equal to 0. Because simply it's a periodic function, right? And then its antiderivative is also periodic, and then you just subtract the antiderivative at the same from each other at the same point. So this integral will vanish, and also this integral will vanish, right? Integral over the cosine 2 theta. Why is that? Well, so 2 pi is also the period for cosine of 2 theta, right? So in fact, this is also true if you put any integer here. So cosine nx for every n, which is 1, 2, it's a positive integer, right? So in fact, it's any integer, 1, 2, 3, 4, etc. This is equal to 0. So what's the answer? We just need to collect all the terms. We just have 1/2 from here and 1 there. So it's r squared 3/2 times 2 pi, which makes it 3 pi r squared. Yeah, so that's the area of this thing. It's 3 pi r squared, which is what, 3 times larger than the area of the disk of the circle. Okay, good. So that's one story. Then let's do one more calculation about the cycloid. Let's calculate the arc length. So we want to know what is the length of this arc, right? In terms of r, in terms of radius. So we know that this distance, we know the horizontal distance is 2 pi r. So we can ask ourselves, what is the length of the arc, right? And we need to remind ourselves how to do how to calculate lengths using methods of calculus. So, okay, well, let's consider some generic example. We have some curve. It may have some intersections. It does something interesting. Right? And so you want to, well, I don't want to do it all everywhere. So say that's, so let's say we have a parametric curve given by x equals x of t, y equals y of t. And let's say we're interested in how did you adjust the bounds in the previous problem? Okay. So bounds have been changed from over here, from 0 to 2 pi r in x variable to 0 to 2 pi in theta variable. That's how they were adjusted. So think about this is theta is just the angle, right? It just, you know, it has no physical dimension, and x is the distance, right? It's like how far you can drive on your car, right? It measured in miles or yards or whatever. And theta is just the angle. So these are two different types of variables. Dana, does it answer your question? Good. Well, there will be another change of variables, I think, in this problem as well. So, and as in previous example, let's say t varies between TA and TB. So, and again, let's say you have point A in the beginning and point B in the end. So point A has coordinates. I'm just going to keep the same notation as before. So point A is x sub A, x sub y sub A. And B has coordinates x sub B, y sub B. And we want to find the length of the curve. So the question, let's call this curve somehow. Let's give it a name, right? Curve C, right? Curve has a name, length of C between points A and B. And so that's what we want to try to understand. Let's say that again. So T changes between T sub A and T sub B, and then here the x of T sub A equals x sub A, y of T sub A is equal to y sub B, y sub A. Right, so in other words, when t is equal to t sub A, we are at point A. When t is equal to t sub B, we are at point B. So we'll need this formula to plug in into the integral after we do the change of variables. X of t sub B is equal to xb. And then in between, so say you go like this. Somewhere here, we have some point, you know, with coordinates x, y, which are functions of t. So t varies, like you go, say, in this direction, right? And then you arrive back to B. Okay, so how do we approach this problem in calculus? Well, first we need to partition our path, our curve, into piecewise linear pieces, right? So into a zigzag path, right? So we can do partition. So the term partition we probably used when you talked about definite integral, right? So we took a partition of the interval AB, right? And then you compute the Riemann sum, compute the area of the rectangles, right? And then in the limit, that gave you the value of the definite integral. So here we want to do the same, only now we are partitioning not the interval in the x-axis, rather we are partitioning the interval in the t-axis. So we are partitioning this interval. Partition interval from TA to TB. We can draw it here again. So this is TA, TB, and then we can sort of break it into small intervals. let's call them T1, T2, T3, etc., Tn minus 1, and then Ta we can identify with T0 and Tb with Tn. So it's a partitional interval, or we can write it as, yeah, so T1 less or equal than T2, less or equal than T3, less or equal than dot dot dot, Tn, which is equal to Tb, and here T0, which is T sub A. Okay. Now you can calculate the image of each of those points. For example, let's take point Ti. Let's say it's here, right? So it will be x sub I, y sub I. Let's say x sub I is equal to x of Ti, y sub I is equal to y of T sub I. And then you do this for every point. Let me not draw all of them. It's kind of, I do a long curve for you, right? And then you connect neighboring points with a straight line. Neighboring in the sense of the curve, right? So you connect xi with xi plus 1 and so on, like this. And all the way till all the way till b. Okay, let's do it here. You see here, this curve has some intersection points, but we don't worry about it because we actually live in the T space, right? It's we only worry about neighboring points in T coordinate. Okay, and then we can calculate the distance between the neighboring points, right? So so you can calculate the Riemann sum, the approximation to the length. So actually maybe I can introduce another variable, maybe it's called AI. So AI is a point with coordinates xi, yi. So here we have A1, A2, A3, and so on. Or somewhere it's AI. So we want to sum the distance from AI to AI plus 1, right? And sum will go from 0 to n minus 1. So that will be the length of this green zigzag path. Or zigzag curve or path. Yep, you can use the word path. It's also synonymous to curve, right? So the kind of the first, that's the. I'm just sort of describing the procedures. So first we do the partition. Second, calculate the Riemann sum. Well, let me not call it Riemann sum. We'll just calculate the following sum. Right, and then third, we take the limit when the mesh of the partition or the number of points on the interval becomes infinite. Takes the limit when n goes to infinity. Let's call the sum Sn, because it depends on n, on the number of segments in the partition. And we expect that if everything is okay, that this Sn goes to L, which is the length of the curve. Question from Julian: why are you multiplying? Oh yeah, I'm not multiplying. It's okay. So this notation is like, it's like the length of the segment. So this is it's like segment between those 2 points. Yeah. Multiplication of 2 points in Euclidean space doesn't really make much sense. We'll talk about vector multiplication later, or dot product. Okay, and now we can just set up the formula. So I hope you'll remember the Pythagorean theorem. So if you have 2 points, EI and AI plus 1, coordinates xi, yi, and this has coordinates xi plus 1, yi plus 1. So this distance is equal to what, right? So then the distance ai plus 1 is equal to the square root of xi plus 1 minus xi squared plus yi plus 1 minus yi squared. Right, simply because if you draw it in the, it's a hypotenuse in the right triangle, right? So and then you just use the Pythagorean theorem, and then we can adopt a notation that we can call this dxi. This we can call delta, actually, right? So it's not infinitesimal yet, it's not small yet. So it's delta xi, this is delta yi, and then our sum, using this notation, we can write our sum as n equals, well, sum of that thing, right? So sum of delta xi squared plus delta yi squared. I goes from 0 to n minus 1. Okay. And now we want to invoke the dependence on the parameter t here, right? So remember that so we want to write it as a sum of the parameter t. So remember that x and y are functions of t. So when the delta x and delta y become small, we can write the following formula that delta xi is equal to the derivative x prime of ti multiplied by delta ti. So delta ti is just, let's also call it delta ti to be a ti plus 1 minus ti, right? It's the length of this segment is kind of part of the partition. Can you please go back to the square root writing? You mean you want this formula, or? Okay, what about it? Do you want to explain it, or you don't see you just want to see the indices? Couldn't see it before. Well, so okay, let's talk about it. Do you understand do you understand the picture, the picture that explains it, right? So if you have 2 points on the plane, right, with coordinates xi and yi, well, then the distance between these 2 points is the length of this green line, right? And then by using Pythagorean theorem, you can show that the square, let's call this, c, a, and b. C squared is equal to a squared plus b squared. That's all that formula says. Okay. Yeah. Okay, and then we continue the formula. So this is an approximate identity. So there's plus some corrections, right? So it's when we have a derivative, then we have dx and dt. But since this is finite difference formula, then there are some corrections here. But it's approximately true. And same true with y. So delta yi is equal to y prime of ti delta, excuse me, delta ti plus some corrections. And then this formula will approximately be equal to, we'll put some approximate sign, but this approximate sign will become exact sign as we take the limit. So the sum I goes from 0 to n minus 1 square root. I'm just substituting here. So it's x prime of ti squared plus y prime of ti squared delta ti. So we took it in front, well, on the back rather, of the square root. I'm unsure what you mean by when you wrote after the delta x delta y line. Oh, you mean the dot dot dot, or? So see here, the exact formula are the following. So dx is equal to x prime of t dt, and dy is equal to y prime of t dt, where dx and dy and dt are differentials, right? So if they're not differentials, if they're not infinitely small but finite, okay, if they're small but not infinitely small, right? Then you cannot technically say that anymore, right? In fact, there will be some stuff here which may which accommodates the difference. In fact, so next class, like maybe next year or something, when you study Taylor formula, you'll be able to write down these terms explicitly. We don't need them for now, but it's just to show that when these are not differentials but finite differences, then the equations are not exact, right? It's like the difference between the tangent line and the graph, right? So this is the same as we discussed it yesterday, right? So if you have a graph, right, and you take 2 points on that graph and connect them, with a straight line, right? Then this straight line is almost a tangent, but not quite, right? And the smaller the closer to each other these 2 points become, the better the tangent, the better this line approximates the tangent. Okay, good. So that's settled now. So it's like a repeating pattern of different segments of different. Yes, that is correct. Yes. So Sharon, can you hear me? Can you guys hear me now? So I see only one complaint about the microphone. Mic sounds good. Good. Okay. Good. Thank you. Yeah. So Sharon, maybe it's just on your side. Maybe you can just hopefully it will go away. If not, let me know. Okay. Good. Right. So we're almost finished with the formula. So that's the approximate formula. But how to make how to make this exact? Now we need to take the limit, right? So as we take the limit, as n goes to infinity, this whole thing becomes the integral, right, from ta to tb square root x prime of t squared. Don't write, yeah, let's write the parentheses. Plus y prime of t squared dt. right? So, well, the reason why it's this is because, well, it's essentially, in a sense, it's a definition of the integral, right? Like it's how you define the Riemann integral, right? You would break it in. So what we just described is 3 steps: first partitioning the interval, then setting up the Riemann sum, and then taking the limit. Sort of, okay, the way it's defined is that, well, you take this limit, and then if the limit exists, then you call this the Riemann integral from TA to TB of, drop my stylus, of this expression. Okay, so let's fix it, and then we'll make maybe a 3-minute break. So the length of the arc, or rather between points A and B is equal to this. So L is equal to integral from TA to TB, square root of, let's write it like this, dx over dt squared plus dy over dt squared dt. Right. Okay, let's maybe make it a 3-minute break or 5-minute break, and then we'll come back and well, yeah, let's continue at 11:10. Right? Yeah, I'll see you guys in a second. Okay, welcome back. So did you figure out the answer to the today's fun problem? Let's scroll back for a second. Oh no, one of you did, but let's not be. So there it is on top. So let's see who is the person. So there's the reason why Amog Gupta was able to answer it so quickly is probably because the pattern is, it should be on the surface. It should be easy to see why this is the case. Also, okay, so what will be, for example, 1, 1, 2, 7. So I think once the answer for this is known, it will be easy to figure out. Okay, so Amog, what will be the answer for 1, 1, 2, 7? If he's around. Zero, yeah. Okay, so do you guys see now? So yes, this is 0. What should I replace? What should I put with instead of the question mark then? So the answer is 5, but why? Okay, so this is 5. Let's do one more. Okay, 8, 8, 8, 1. What is that? Okay, so Amok, I think we need one more hint from you. Yep, that's 6. Do you guys see the pattern now? Why 8840 is 5 and 8881 is 6. Nope, LOL. Okay, we still have. It's like the movie. Which movie? Imitation Game. Well, it's much easier than the Enigma code. Trust me. It's like if that was the Enigma code, the Germans would lost the first day. No. Yeah. Okay, so we still have 45 minutes. If you want to do it, you can submit the answer during office hours. I can write it down. Okay, so let's do an example with the length of the arc. So let's do our favorite curve, the cycloid. Or maybe let's do the circle first. Like let's check the formula actually makes sense, right? So first example, and if you practice overall in general, if you're trying to to do a calculation, let's do a circle. So you make a you make some simple check that the formula actually works. So let's say x is equal to r times cosine theta, y is equal to r times sine theta, and theta varies between 0 and 2 pi. Okay, well, we know what the circle is, right? And the formula set suggests that the length or its circumference equals integral from 0 to 2 pi, square root of r times minus sine theta squared plus r, r times cosine theta, everything squared. Oops. D theta, or it is also equal to r squared Was it a koan? What's koan? I'm not sure which language is that. But we have like O with the bar on top of it. I'm not sure. No, I mean, I think that what you're referring to should be much more sophisticated than what I'm asking. So once you solve it, you'll see how easy that was. I mean, it's again, it's a prank, so that there is a catch. Right. So then here, this is equal to 1. So the answer is equal to. Oh, sorry. There's no r squared. Nobody is watching my formula, right? So it's r, right? So under the square root, you have r squared. So you take it up front to get r. It's equal to 2 pi r. Okay. Julian is watching. Very good. So the answer is correct. Yes. So the construction works. Now let's do the cycloid. And it's another example of a cycloid. Write down the formula again. So x is equal to r theta minus sine theta. Y is equal to r 1 minus cosine theta. Let's calculate derivatives. X prime is equal to r 1 minus cosine theta. We already did it, but r times sine theta. And now the right, so cycloid is that, and then theta varies between also 0 and 2 pi. So the length is equal to r squared 1 minus cosine theta squared plus r squared sine theta squared d theta, which gives r can be brought up front again. 1 minus 2 cosine theta plus cosine squared theta plus sine squared theta. Again, we can combine this into 1. And the integral will be r square root 2 integral 0 to 2 pi 1 minus cosine theta. Okay, I'll check that link later. then yeah, so, and we can, again, use one of the trigonometric identities. Actually, let me not take out square root 2. It's not necessary. I'm just gonna keep 2 inside. So it's 2 minus 2 cosine theta, and we can use the doubling angle, right? So the doubling formula. So 1 minus cosine theta is equal to what is it? Twice, right? Sine squared theta half. That's a reminder how this works. So it's equal to r, integral from 0 to 2 pi, square root is 4, sine squared theta over 2, d theta. And also we can take out the square root. So in principle, we should, when we take this root, we need to use the absolute value. But sine theta half, when theta varies between 0 and 2 pi, is always positive. Because, sine theta, so sine theta is this, but sine theta half is that. So it's always positive. So we don't have to worry about the sign. R times 2 sine theta half d theta. Right, and then, well, to integrate that, well, we just integral of sine of theta half is minus 2 cosine theta half, and we need to substitute between 0 and 2 pi. That finally brings us, so when theta half is equal, cosine of pi is minus 1, right? So it's equal to 2r, and so it's 2 minus 2. Right, because cosine of 0 is equal to 1, and then there's a minus here, and this is minus from the formula. So overall, it's equal to 8r. Right, so that's the arc length of the cycloid. Okay. Right, and then, like I said, so I invite you to solve the homework, problems in homework to get more practice. Then one more story for today will be the surface areas. So it requires, in order to calculate surface areas of surfaces in 3 dimensions, we need to know a little bit more, right? So we need to, well, I mean, we just need to generalize the idea of to 1 dimension higher, right? So in principle, we would need to take a partition of some part of the plane and then construct Riemann sums and calculate the area. We'll do it later in the course. Instead, now let's consider a very specific type of surfaces which are obtained by rotation of graphs with respect to the x-axis. So consider, again, let's take our favorite cycloid or anything like this, so that there's a shape, and then it's x-axis and y-axis, and then what we're doing, we are rotating this in the everything around the x-axis, and then you would remember each position of the graph, right? So it would in this case, it will look like a cocoon of some sort, right? So it will become a surface which looks like a football, right, or cocoon, whichever you want to call it. So we want to find the area of this. Right. And well, we'll do it because it's a very small, tiny generalization of what we're doing now. Good. Is this 3D? Good. So it's a 3D shape, right? So it's actually, you would have to put another axis here. So yes, so think literally of a surface of a football. And you take a football and then you want to calculate its area. So you know that the football is the it has the axial symmetry, right? So it's symmetric as you spin it around its axis, and that's why, you know, so in football you can actually throw it very high, right? So you know, when probably some of you know this better than me, right? So maybe some of you play football semi-professionally. So when a quarterback or somebody is throwing the football, like they would put their fingers on the seam, right? And then they use it to spin the football around its axis. And then the reason why it's sort of it's symmetric, it's axial symmetric, it gives it extra stability when it flies, right? So like the torque, the extra momentum, that it generates, it gives it stability, so it can travel far. Like it will fly much farther when it's spinning than if you just try to throw it without it. You can try it. So it's a 3D shape, but we're calculating the surface area of it. Okay. So how shall we do this? First, let's take a simpler example. Let's say it's not a football, but an actual cylinder. So we take a segment from A to B. Let's see, this is just a piece of horizontal straight line between A and B, and then its y coordinate is equal to r, right? Because it will become a radius of the cylinder. And then we'll rotate the shape around the x-axis. What will we get? Well, we'll get a cylinder, right? We'll get a cylindrical shape. Like that. Try to make a better picture. So it's now using 2 dimensions with the surface of the cylinder. Okay, now if the radius is r, we know that circumference, the length of the side. So the circumference is equal to 2 pi r, right? And you can, in fact, take the cylinder and you can unroll it, right? You can sort of unfold it and put it as a rectangle. So it will be a rectangle of sides r and 2 pi r. So the surface area of this cylinder is equal to just the product of the sides, right? Of the product of 2 pi r times r, which is 2 pi r squared. Okay. And now, well, we want to use this idea to calculate something that looks like that. So what we're doing, we take so the idea is to foliate our shape into the small cylinders, and then calculate area of each cylinder individually, and then connect them together. So between these two green marks, we'll have a small cylinder. Should make probably a bigger picture. Okay, so it looks like, so there's one plate and then there's another. Right, so there's a point, say, xi and xi plus 1. So the area of the small cylinder, you can call delta area, delta A, is equal to 2 pi yi, right? Well, one sec, I'll go back to that in a moment. So let's say this cylinder has like this little piece, a little segment has coordinate yi. So that's the radius of that cylinder. And the length, this side is delta xi. And so delta xi is xi plus 1 minus xi. So this is delta A is equal to 2 pi yi times delta xi. So it's exactly the same formula as here. Only here the R. Excuse me. Yeah, you're right. I'm sorry. It makes no sense. So we're already getting tired, right? So you need to multiply it by the side, right? So it's 2 pi r multiplied by b minus a. Yeah, thank you. Right. So the length of this side is b minus a, right? The circumference of the top of bottom boundary of the cylinder is 2 pi r. So the area is 2 pi r times b minus a. Okay. Right. And then here it will be equal to, in green, it's 2 pi yi times delta xi. Yes, thank you. And then so you can sort of see that the idea is to kind of to foliate our shape into the small cylinders and then take the sum over their areas. So we can approximate, again, we can compose a sum, let's also call it Sn, which is a sum of n goes from 0 to n minus 1 at 2 pi yi delta xi. And then as we send the number of the small cylinders to infinity, this will approach the integral from, well, let's call it the, well, let's just go from a to b, right? Integral from a to b, 2 pi y dx. Right. But now, I think I just did something different. So yeah, it should be y dx, and then one second. We actually want to do it slightly differently, not the dx, but using like the cone, using the surface of the cone. Can we still do it like this? 1 second. Yeah, that should work. Yeah, I'm sorry. Right. So right. So and then well, we can use this formula to calculate. So how is it for the Sorry, just 1 second. Right, yeah. Okay, so the and then yeah. So let's try to calculate the surface area of the ball, right? So the it should be dl. I'm just trying to see where's my what did I do wrong, right? So the formula, which I think should be the case, instead of dx, it should be it should be ds, right? Yeah, okay. Let's correct over here, right? So ds, and then here the yes. I think I went a little bit too fast here. What we actually should write is that d delta x squared. Let's write it again. Yeah, so it's square root of delta xi squared plus delta y squared. So the reason for this is the following. So you should actually look at not at yeah, that's right. It will be more precise if you look at not at the cylinders, but at cones, at parts of the surface of the cone. Yeah. Okay. Sure. Yeah. I'm going to repeat everything. Okay. So let me do it again. In fact, let me just delete this. Yes, we have time. Okay. Yeah, sure. So I just reading the request for me to slow it down a bit. But Sharon, just for information, you don't have to write it. The video is available online, so you can just watch now, and then you can you don't have to make notes as I speak. Like also, I will send you the PDF, like all these lecture notes. Like so I'll convert this into a PDF and send it to you all. I'll just upload it to the courses. Yeah. Okay, so let's do it here. So in fact, yeah, the idea is that, say you have a surface of rotation like that, and then you want to make it like yeah. So now it looks more or less symmetric. Okay, now so we have 2 points here. Xi and xi plus 1. Right, and then we just draw disks which are vertical and sort of cross the x-axis to that point, and then consider this green surface of a cone right over here. Right, so then what we actually need to do, we need to consider the so this point has coordinates xi, yi, and this point has coordinates xi plus 1, yi plus 1, right? And then the area of the green cone, so this delta A I looks like what it looks like. We can write it approximately as 2 pi yi, right, multiplied by square root of delta xi squared plus delta yi squared, right? So this is the delta S fi. Sorry. This is delta fi, which is sort of this distance over here. Okay. So yeah, it shows you approximately the area of the segment, right? And now we need to calculate the area of the whole rotational surface. You need to take the sum, right? So the full area will be the sum from I goes from 0 to n minus 1 delta ai, which is sum as 2 pi yi square root of delta xi squared plus delta yi squared. Okay, and now the again, similar to what we did with the path, we want to recall that the surface, this curve here, right, is given by it's a parametric curve, right? So we know that x is equal to x of t, and y is equal to y of t. So dx is equal to x prime of t dt, dy is equal to y prime of t dt. So therefore, as we take the limit, n goes to infinity, when the distance, the mesh of the partition becomes smaller and the number of the subpartitions becomes large, then we get the so the sum becomes, area becomes integral from say a to b, or other, so let's do ta to b as before, sorry. So ta to tb, and here t varies between tb and ta, and this is 2 pi y of t square root dx over dt squared plus dy over dt squared dt. Yeah, this is the formula. Question from Julian: why is that yi in front of the square root constant? Does the distance formula account for the change in height? Yeah, so like it's the when you have a surface, say you have this thing. Well, let me draw the cone which looks upright, like this, right? So say you have a cone surface, and say this is what you actually need to do. You need to take the medium distance. So that's why I said it's an approximate formula. So what you actually need to do is you need to take the average, right? So if this is yi and this is yi plus 1, so the area is equal to, we need to take a cross section at the middle over here, right? And then take this thing which is the average, yi plus 1 over 2. But because the cone is very small, it doesn't really matter where you do it. So I mean, yi plus 1 is not much different than yi. So you can take the middle point, you can take the left point, you can take the right point. It's like when you compute the integral, the Riemann integral of the function of one variable. It's more or less up to you where you put where you evaluate the function, right? So if we say this is your function, right, and then you draw your rectangles, it's up to you where which height of those rectangles you pick. You can have this point on the left side, on the right side, or in the middle. if the function is integrable, all limits, all Riemann sums will converge to the same integral. Same idea here. That's right. Other questions? Basically, yeah, so the we're simply summing up the surface areas of the columns to get this formula, which now works explicitly. Okay, so let's do the final calculations, another calculations with the cycloid. By now we should probably know it by heart what the formula, what the curve looks like. Sorry. Yeah, so example, yes, x is equal to r times theta minus sine theta, and then y is equal to r 1 minus cosine theta. Again, it's derivatives. X prime is r 1 minus cosine theta. We did this calculation. We could just pull up our formula from before, right? So this when you substitute the square root, let's pull up the calculation from above, right? So we don't have to do it again. So this, right, is the square root that we need for the calculation. So we know that the integrand in this case equals to r times 2 sine theta over 2. And the so yeah. I hope we can still do the integral. Yes, so the area, so it's integral from 0 to 2 pi r multiplied by of 2 pi times r 1 minus cosine theta multiplied by twice sine theta over 2 d theta, right? And then there is some trigonometric to r. And so let's collect things together. So it's integral from, no, not to pi r, to pi. 0 to 2 pi, like this. So it's equal to 2 pi, well, let's collect all the terms. It's equal to what? 4 pi r squared, integral from 0 to 2 pi, 1 minus cosine theta, which is equal to what? It's equal to 1 minus cosine theta. It's, again, it's twice sine theta over 2. And then there's another sine theta over 2. So that gives us what? It gives us 8 pi r squared, integral from 0 to 2 pi, sine squared theta over 2. And then we need to use the doubling form, the trigonometric formula again. So sine squared theta over 2 gives us a, what is it? It's 1 minus a, it's 1 plus cosine theta over 2, right? And then as we integrate cosine over the period, we'll get 0. So the only contribution from here will come from the 1/2. So the answer will be 8 pi r squared times 1/2 times 2 pi. And finally, that leaves us with 8 pi squared r squared. Yeah, that's it. Just a little bit more calculation because the well, there's extra function here in the integrand. There's y multiplied by square root. Good. Yeah, so that's another application of parametric curves. So you can easily calculate the surface area of the rotational shapes that have axial symmetry. Analogously, you can find areas of the shapes that are obtained from rotation about the y-axis. Right. So here, because we're doing parameterization, we're studying parametric curves. For us, it doesn't really matter too much whether what is x and what is y. Right. We can always switch them around and adopt this calculation. Questions from Amok. Was the surface area? Was that the surface area of the 3D cycloid? I'm not sure what 3D cycloid is. Do you know what's the 3D cycloid? So yes, this is it was the surface area of one segment of the 2D cycloid if you rotate it around the x-axis. Yeah, which is yes, it's a cheap way to obtain 3D shapes from 2D shapes just by applying the rotational symmetry. Hannah is saying, if it's rotated about the y-axis, would x of t be that is correct. Yes. So I was about to comment on this. Yes, thank you. So now, what if you rotate about the y-axis? So then we just need to consider that we need to treat our cylinders differently, right? So the try to make a shape. Maybe it looks like a black hole or something. Well, not quite a black hole. Anyhow, shape like that, which is a symmetry rotation about the y-axis. As Hannah is saying, what you need to do now is to slice it with conics like that, right? And then the delta AI would look like 2 pi xi multiplied by delta si. Which is, of course, 2 pi xi square root of delta xi squared plus delta yi squared. And that translates also into the integral. So you would integrate now between TA and TB, 2 pi x root dx over dt squared plus dy over dt squared dt. Right. The distance formula wouldn't change, right? Because the ordering, yeah, absolutely, yeah. So the distance formula only worries about the parameterization, right? So once you pick the parameterization in T, it's all fixed. Okay. Good. Yeah, so I think we had a lot of a big selection of topics today. I think we should stop here. So all right, so there will be office hours at 2. I'll make another announcement in B courses. You're welcome to bring your homework questions or whichever questions you like. If there are no, I'll upload the whole PDF, what I'm doing right now, into B courses. So I think under the folder files, I put like lecture notes, like so special subfolder lecture notes, and I will constantly be updating this. Like everything you see here will be there. So I think the sort of the right strategy to listen to this lecture is not to take notes while you're doing this. You can just watch the screen. It's like a movie, right? So it's like watching a YouTube video, only you can interact with the speaker. This way it's better than the YouTube video. And I think during the discussion we can actually unmute ourselves. We can show your videos, and we can have an actual discussion which is close to real life. It is only 10.2. I think also 10, yeah. So we just finished 10.2. So tomorrow we'll do 10.3 and 10.4. Yeah, that's right. So I think we will go a little bit faster tomorrow. It needed maybe a lecture for a little bit on Friday, but so given the fact that this week there is no quiz, well, it's okay. So you know, we're just trying to figure out the right pace for the lecturing. Will you update the answer key for even homework questions? So I don't have that here, so neither do my TAs. But so if you have you can always, if it's a computational thing, you can always check it on a computer, like on Mathematica. If no, you can ask me a question. So yeah, I don't currently have answers to the homework problems. All Friday classes will be discussion. Yes, that's the goal. So you're welcome to. We'll solve some problems in class, like in a discussion, and you can bring your questions. There will be like Q&A session as well. Okay. Sure. Yeah. So it's a bit. Yeah. I also found that when I give even like a talk, like not lecture, but a research talk on Zoom, it somehow goes a bit slower even then. But that's sort of the specifics. Okay. Okay, so we have 2 minutes left. And did anybody figure out the pattern? Except one person. Where is it? Okay, yeah. So if not, we can discuss it today, or like during office hours if you come, or tomorrow. So for office hours, use the same link, the same Zoom link as before. Okay. It's similar to calculus. Well, I don't think actually this pattern is not similar to calculus. It's actually not. Yeah, the number of circles. Yep, that's right. Yeah, so Bennett figured it out. Yeah, so it's really the number of circles, or rather closed loops in the numbers. So you see here, the reason why 8881 is 6 is because 8 has 2 loops and there are 3 8s. So this is 6. Now 1127 is 0 because there are no loops in numbers. 8840 is 5 because there are 5 loops, etc. Yeah, so in fact, that it's not something that we just made up. It's in topology, kind of this idea. It brings us to the notion of the fundamental group. Of the topological space. So in a nutshell, fundamental group, it counts, well, how many non-contractible cycles your space has. So if you think of these numbers as shapes, like as the sort of one-dimensional spaces, if you put them together, the fundamental group of each of the spaces will have that many generators as written in the right column. So 2789, it has 3 loops. So that's why the answer is 3. Yes, that is correct. Very good. Okay, good. Thanks, guys, for listening. So we'll see you later. See you tomorrow or during office hours. Thanks. Bye.